Howdy. The purpose of this video is to review some of the basic terminology that you would encounter when you're talking about mechanical properties in materials. And we're going to focus this all around a stress-strain diagram, as that's one of the principal tools that we use to interpret mechanical properties in materials. Now, I'm going to assume that you've already watched the video or read about stress and strain. As a quick reminder, stress is defined as force per unit area, and we typically illustrate this on the vertical axis of the stress-strain diagram. Strain we show on the horizontal axis, and that's defined as a change in length per total length of material. Also, this is engineering stress and strain we're showing, and we're going to be talking about tensile stress-strain diagrams, which means that we're pulling a material along one axis, so that would be a tensile stress. You could create a stress-strain diagram for compressive stress and strain as well. Now, we talked about stress and strain. The first thing that I want to talk about is the difference between elastic behavior and plastic behavior. So if you look at stress-strain diagrams, typically we find fairly linear regions at low strain. And this is the elastic portion of the chart. If I stress a material, I have some deformation. But if I remove that stress, I come back along this same path. And that's what makes it elastic. It's recoverable. Now, somewhere out here, we've gone off that linear path. And so if I was to deform a material all the way out to here, I'm applying a lot of stress now. If I remove that stress, I have some irrecoverable strain. And so that would be the plastic deformation. So somewhere in here, there's a distinction between this elastic and plastic deformation. So let's look at that in a little bit more detail. There are a couple terminology and points that I want you to be familiar with. I'm going to draw a representative stress-strain diagram, and I see that the way I drew it, it looks pretty linear in here, but it starts to deviate from linearity about this point. So this is called the proportional limit. The proportional limit is defined as the point at which we're no longer proportional. We're deviating from linearity. So if I was to extend that line, it would look something like that. Now, oftentimes it's very difficult to pinpoint one distinctive stress at which this proportional limit occurs. So let me draw a second line, and we'll make it a different color here. So if I was to draw a line that looked more like this, you know, it's very difficult to say in there where exactly did I deviate from linearity. Was it here? Was it here? So we use a convention to illustrate where we're going from elastic to plastic transformation. And the way this convention works is that we start off on the horizontal axis at 0.002 strain. And so this is just a number that's agreed upon and commonly used. Sometimes people would use other numbers, but we'll use this one. So that's the same as 0.2% strain, so some very small strain. And the next thing I do is I'm going to draw a line with the same slope as this line coming out of the origin. But here I'm going to make it a perfect line. So I could use a ruler, I could use a graphing tool, but I know that's going to be a perfect line. And at some point, these two lines intersect. And so this is what is commonly referred to as a yield stress, a yield point, or a yield strength of a material. And the reason, again, that we use this convention is that it's very difficult sometimes to identify some specific point where it deviates from linearity. Now, that's not always true. You know, some stress-strain diagrams might be very distinct, and then it's easier to say, yes, the yield stress is here. But I would encourage you to use this convention whenever possible. Okay, one other thing that you should be aware of is that certain steels exhibit a very interesting phenomenon called yield point phenomenon. And so I'm just going to make a new axis here. So what occurs is, again, we have elastic behavior. We start to exhibit plastic deformation, but then there's a drop, and there's a bit of a random stress that a material can withstand. and then it'll continue to increase and plastically deform from there. So if I see this kind of behavior, this is usually called the upper yield point, and the lower yield point. And usually, if I were to pick a yield stress for this material, I would pick that lower yield point because, once it goes past this upper yield point, this is now the new yield stress of the material. So this is a behavior we don't see in all materials, but it's something I would like you to be familiar with. Okay, one other thing that we should think about is in this elastic region. So again, I have a nice linear region here. I can define what's called the elastic modulus. And this is a very specific elastic modulus. This is the Young's elastic modulus. Or sometimes it's called the tensile elastic modulus, if I'm looking at a tensile stress strain diagram. And so because it's linear, we can we can say that stress is proportional to strain, and they're proportional by some constant that we call the Young's elastic modulus. And so if I were to rearrange this, I can see that the elastic modulus is just given by the stress over the strain, which is just a slope, right? Stress is on our vertical axis, strain is on our horizontal axis. So rise over run, I can find the elastic modulus of a material just by looking at the slope of that initial linear section. Now, again, remember, materials are not always perfect. And so in some cases, we might have something which is elastic. It behaves elastically, so it's totally recoverable, but it's not perfectly linear. So in this case, if I applied some stress, I could come up here, but I could still recover all of that stress, all of that strain upon removing the stress. So it's not linear, so how do we find a slope for it? There are two different things we can do. We can draw a line from, say I want the elastic modulus at this point. I could draw a line from the origin through that point, and that's what we would call the secant elastic modulus. Or I could look at the specific slope of that line at that point, and that's what I would call the tangent elastic modulus. So again, nature isn't perfect. We try and make it perfect by our models, but these are the terminologies that you would need to know to discuss elastic behavior in materials. Okay, so we've talked about the elastic portion, so what's going on down here. What is some terminology you might need for the other important points on this diagram? So this label here, sigma sub u, this is the ultimate stress or ultimate strength of a material. I should mention that this is kind of a typical curve for metal that we're looking at. So usually this point is associated with necking, and we'll talk about necking at some future point. But this is called the ultimate stress. That's the maximum of the stress strain curve. And finally, this is called the failure point, the failure stress, failure strength. This would be the failure strain point. And this is when the material actually breaks entirely on you. So this is a very important point in terms of what's happening under extreme plastic deformation. One thing that we often talk about in materials is their ductility. How much can they deform before they break? And so one measure of ductility is the percent elongation at failure. And that is exactly what the failure strain is, right? So a percent elongation would be delta L over L times 100. And strain, again, remember, is just delta L over L. So that is ductility. One other thing that I wanted to talk about, I guess we're using the same graph, we can talk about how much energy it takes to either break a material or how much energy can be stored elastically. And how we do that is by integrating different areas of the stress-strain diagram. So if I were to integrate the stress-strain curve from integrate stress d-strain from 0 to the yield point, I would get this area here, and this is usually called the modulus of resilience. And so this tells us how much energy can a material store elastically. If I were to integrate the entire area under the curve, so from 0 up to the failure, sorry, this should be strain, up to the failure strain, again, stress d-strain, if I get the area under that whole curve, that's a measure of how much energy it takes to break the material. Now this would be a kind of a static measure of that because these are usually captured by deforming a material very slowly. There are other ways to measure this toughness. So this is the modulus of toughness. There are other ways to measure the toughness by a more dynamic experiment. So essentially swinging down a heavy weight and breaking a material. And those two give related toughness. Okay, so in review, we talked about definitions. We talked about stress and strain, proportional limit, yield stress, yield point, elastic limit. We talked about the Young's modulus, which is also referred to as Young's tensile modulus. We talked about ultimate stress and strength, failure stress strength, which is also defined as the rupture point sometimes. And we talked about ductility. And finally, we talked about modulus of toughness and modulus of resilience.